and the position vector ip. So the total torque, we write it as ig into alpha. So now in the last session we have seen how we can resolve this vector torque, and both are vector equations. Okay, so both are vector equations. So we write in scalar format, like by taking the x component and y component for the first equation, and for the second equation we resolve the vector equation into the scalar equation. So we expand the cross product here and cross product here, and I've shown you how we can write R12 cross F12 as like this. So similarly RP cross FP we can write like this. So now these are the three scalar equations, and these three scalar equations we can write in matrix format. Okay, so this is the unknowns are F12x, F12y, and R12. So this is something like a matrix inversion. So if this is the final form for the force analysis. For a simple link, for a single link, or for a two link system. Okay, so you have minimum two links, one ground and link 2, which is a ground. So for one link you have three equations. Now the same thing when you extend to a 3-bar mechanism. Okay, so 3-link system, as you can see here, there is a ground link, there is a link 2, and there is a link 3. Right? So in this case, you need to draw the free body diagram for each link. So ground link, always you will have a force acting on 1, 2, and the force acting on 2, 1. So they are equal and opposite forces. So similarly, link 2, as we have done in the previous case, so you have two forces and there is an external torque. So you can write three scalar equations here. So similarly for link 3, okay, so you can draw for link 3 also similar scalar equations. So in whatever the link, there are only two equations, vector equations. So sum of the forces is mass times acceleration, and sum of the torques is Ig. So where I is the moment of inertia. Okay, I into alpha. Alpha is the angular acceleration. So in this case, so there are two grounds. So there's one ground you are drawing the free body diagram for this. So similarly, the ground which the crank is connected, so we are drawing the free body diagram. So for this, so we can see each link, we have the three set of equations. So finally consolidate all the equations and write in the matrix format. Okay, so this will be, now this is a slider crank mechanism. So here you have the 4-bar linkage mechanism. Okay, if there is a friction coefficient is given, and you can see instead of 9 equations, so you end up getting 8 equations. So for link 2, so you can see the 3 equations. Then for link 3, you will have 3 equations. And for the slider, actually you can consolidate these 3 equations into 2 equations. So finally you have, okay, so this 8 by 8 matrix. Okay. So normally in the exams, so you will be asked to derive the force equation for any 4-bar linkage mechanism. It doesn't matter, it may be a slider crank or it may be something different. But whatever it may be, your free body diagrams look like this. So similarly, just like each link separately out, draw the free body diagram, then apply the sum of the forces equation, sum of the torques equation, then those are the vector equations. So convert the vector equations into scalar equation. So the procedure is fairly standard. Okay, so out of 20 marks, so you can score good marks if you can do correctly. So even if you draw free body diagrams and whatever you do it, you still can get good marks. Okay, this may not be true when you do the other 2 questions, which are identifying instantaneous centers or calculating the velocities and acceleration polygons. So there, if you're good enough, if you understood the principles, you can score full marks. There's no doubt about it. But this question and balancing question, that's where everybody can score marks. And okay, you need to practice a bit, that's all. And follow the pre-exam workshop closely. And no one should miss the pre-exam workshop. All right. So after the force analysis, then we move on to balancing. So in the other question will be asked will be from balancing. Okay. So balancing is always the question comes from either dynamic balancing or so inline engine balancing. So in the last session, we have done some questions, by drawing some of the movements to 0. That means movement MRL polygon, and then drawing MR polygon. So by drawing those two polygons, you can easily do the balancing equation. Okay. So the next question you can do very easily for 20 marks will be from balancing. Okay. So balancing, the concept is, you have to make sure that the sum of the masses, okay, the centroids, so should coincide with the axis of rotation for perfect balancing. So now if you see here that link, okay, so this is the centroid for link 1 and this is the centroid for link 2, and the system centroid is here, and the axis of rotation is here. So therefore, when it is rotating, okay, so it creates a lot of vibrations and noise, and the system is not balanced. So to balance the system, you need to to create a contract mass, okay, a contracting or balancing mass, and make sure the centroid of the entire system lies with the axis of rotation. Okay, so to do this, what we need to do is we have to make some of the forces acting on the system will be 0. So we need to adapt this equation. From this equation, so we'll be able to find out this MBRB, so the x component. Okay, this is a vector equation. So we again write the scalar equation in terms of x component and y component. Okay. So for balancing questions, R1 will be given, M1 will be given. So masses and the radii. Okay, so this is the radii, R1 or Ri. So what you need to calculate is MBRB, so the mass of the balancing mass, and the radius of the balancing mass. So this is the radius of the balancing mass. So you can do analytically by just calculating the x components and y components like this, because R1, the orientation θ1, θ2, So therefore R1x is simply R1 into cosine θ1. So R1y is simply R1 into sine θ1. So you'll be able to calculate these two. So from here, you can calculate the MBRB as from this formula. Okay, then the angle for the balancing mass θB you can calculate from this formula. And alternatively, you can also do this very easily by plotting MR polygon. So we have done that in the last session. So for example, here we are seeing, so we have done some problems related to MR polygons. So that is simply static balancing. But normally we have those linkage systems, okay, rotating in a plane. So therefore we have to balance not only the forces but also the movements acting on the system. So for dynamic balancing, we need to make sure the sum of forces acting on the system to 0 and sum of movements acting on the system to 0. Okay, so this is an example of say there's a mass here, this is R1 is the position. So the force acting here, okay, M1 R1 omega square. Now in a plane view, so you can see the M1 R1, M1 and M2 are located like this. Okay, so now with respect to okay, so now you can see here a three masses M1, M2, M3, right? So M1, this is called the plane A, plane B. So this is where we are putting some balancing masses, okay, for dynamic balancing. Okay. So here the unknowns will be MA, MB, and also this LB. So L1 will be given to you. So L1 is the distance from plane A to mass 1. Similarly L2, plane A to mass 2. L3, plane A to mass 3. So the same L1, L2, L3, when we plot, we are calling them as R. Okay? Yeah. So LB, so these are the perpendicular distances for the masses from the correction plane A and B. Okay, so in plane view, you can see the location. So the angles will be given theta 1, theta 2, theta 3. So now we have to first sum the forces to 0 acting on the system. So similarly, you have two masses, right? MA and MB. Okay, so you get two equations here. Now you can, now we are summing the moments to 0, sum of the moments acting on the system to 0. So we take with reference to plane A, so we make the moments with respect to plane A to 0, then you can calculate the moments due to plane B. So this is the force, and LB is the horizontal distance from plane A to mass, plane B. So this is the moment due to mass 1, moment due to mass 2, moment due to mass 3. Okay, so from this you can calculate the x component of MBRB. So you can see omega square you can take out from all the terms. Right? So similarly, you can write it NB, RB, Y. So when you want to do analytical calculation, we just use these equations. Okay. So now let us do an example. This one we've done in the class, so I give you another one. Okay, so dynamic balance. So let us say the angular velocity is given as 750 revolutions per minute. So M1 is given, M2 is given, M3 is given. So let us say M1 is 12 kg, M2 is 3 kg, and M3 is 10 kg. So we also know the positions of masses R1, R2, R3. So R1 is 0.2 meters, R2 is 0.3 meters, R2. R3 is 0.15 meters. So the positions of the systems in the XY coordinate system are so mass 1 is located along x-axis. So mass 2 is located in negative x, y plane. So this angle is 45 degrees. Okay, M3 is located here. So this angle is given 150 degrees. we have the two correction planes A and B. Here we have the two correction planes A and B. Now the distance from A to M2 so this is 0.3 meters. And this is 0.2 meters. So now we have to calculate this MA, RA, MB, R. Okay, so this is all given data including the sketches. Okay, so now what we can calculate? So we can calculate the forces acting on the three masses. So we can calculate what is F1, F2, F3. So we can calculate the force acting on mass 1 is, so we can write M1, R1, omega square. So similarly, F2 we can calculate M2, R2, omega square. So F3 is similarly M3, R3, omega square. So omega is given as 750 revolutions per minute. So you need to convert that into radians per second. So omega convert into radians per second. Then you know F1, R1, so you can calculate F1, F2, F3. So let me know once you calculate F1. So 750 revolutions per minute is equal to
78.54.
78.5 radian per second. So any answer for F1, F2, F3? M1 is 12 kg, R1 is 0.2, your omega square. Yes,
14,804.
so you can round it out to 14.8 kilonewtons, right?
Yep.
So what about F2?
5.551. 5.55.
5.5?
Yeah, 5.6.
I think I have 5.55. So F3?
9.252.
Yeah. So 9.24 kilonewtons. So these are the F1, F2, F3. But now we can resolve these forces into the X component and Y component. So you can see the mass 1 is along x-axis, so it has no y component. So we can write F1x is equal to 14.8 kilonewtons and F1y is 0. So similarly F2x, so the x component of the force will be, so you can write the magnitude of the force is 5.55. So multiplied by cosine of, okay, so you can see M2 is here, okay. So total angle is to calculate the x component. So we take angle with reference to x-axis. So that will be 90 plus 45, so that is 135 degrees. And similarly, F2y will be 5.55 into sine 135. So how much you get F2x, F2y? So F2x, how much you get? Is this negative 3.92? F2y? Plus 3.9. So the force will be in this direction. So the force of 2 along x-axis will be negative. Okay. So the force of this along y-axis will be positive. Okay. So because M2 is in negative x and y plane. Okay. So the x component is negative, the y component is positive. So now with this, the 3x, so again x component will be negative for this, and also the y component will be negative. So if you consider the force acting here, F3, so F3x is negative, and F3y is also negative. Okay. So F3x is how much? Negative negative 8.00 kilometers. So F3Y is negative 4.62 kilometers. Alright, so now we have the force components along x and along y. So now we can calculate the movements because we know the distances, okay, to the plane A and plane B. So we can sum the movements with respect to plane A. So therefore, we can write so summing the movements so with respect to plane A. So we can write now the x component of the balancing force at B, the x component of the balancing force at B as negative F1x into L1, negative F2x into L2, negative F3x into L3 over, so the total distance from A to B. So from A to B the distance is 0.5. So you can write this as LB. So similarly, we can write the balancing force at B, the y component. So you can write negative F1y, negative F2y, negative F3y into. Okay. So this is the distance, which is 0.3 meters over 0.5. So you can see all L1 and 2 and 3 will be 0.3 meters. So from this calculate what is FBX and FBY. So your L1, L2, L3 is all 0.3. So any answer for FBX?
What's LB again?
0.5. LB is the distance from A to B.
Oh.
Because we are taking the movement with respect to A.
Oh.
Okay? And L1, L2, L3 will be all 0.3.
FBX is 0.5 times LBX.
Say again, which one?
FBX is 0.5 times LB.
No. This 0.5 is nothing but LB.
Okay.
When I wrote, I said, because probably you may be asking what is this 0.5. So I just 0.5 is the distance between plane A to plane B. So here also is so you can see it takes longer time compared to plotting MRL. Now the same problem you can do using plotting the MRL coordinates and the MR coordinates. So here we just calculate the balancing forces. Then once you know balancing force, you can know MB, RB, MA, RB. What is LBS?
Negative 1.17.
Negative 1.7.
17.
So my answer is 1.728. FB1?
FB1 is
0.42.
Yes, betul lah.
Then FB will be, you get about 1.78 kilometers. So this is the balancing force required at plane B. You agree with the values? So once you know force B, then you can calculate force A. The balancing force at A will be negative of F1, negative of F2, negative of F3, negative of FB. So you can simply calculate the sum of the forces F1, F2, FB. So these are the balancing forces required. Now, what should be the mass? Because we know F is equal to mr omega square. Okay? And omega is known. Okay? So force is known. So therefore you can find out M-A-R-A. Okay. So MARA will be the design parameters. So the designer can choose what mass to use at what position to use. Okay. So similarly from FB you can calculate MB RB. So from FB you calculate the product of mass B and RB. Because FB is nothing but MB RB omega square. So we know omega square, we know FB. So we can only find out the product M and R. So normally there are people who design the things so they can see that they can play with it. So depending on ergonomics, depending on the other things, okay, the dimensions required, so they can play, they can increase the mass, they can decrease the radius. Okay? So this is how when you apply the analytical calculations, you know the analytical calculations routinely you can do. Okay, all these equations you can find in the slides, okay, which I already uploaded. What is the FA value? I think you get about 4.62 kilonewtons. No? So in the exam there will be a question on balancing of masses. So it may be from dynamic balancing or there is another topic which we discuss now. So from one of the topics. So if the question comes from dynamic balancing, you can use the MRL method or you can use the calculations method. Say again? FA, because you know F1, F2, F3, right? You have already calculated.
Yeah, correct.
Then FB also is calculated, right? So F1 is 14.8. Is it 9031?
Yeah, I
Yeah.
got negative 31 also.
So you can correct this. Kilometers. Alright, so so next we move on to the last topic, so which is the balancing of inline engines. Okay, so balancing of inline engines. So what we are doing here, I first take you to the figure here. So here you can see. Okay, so the 3-cylinder engine, so the front view, okay, so you can see the cylinder 1, cylinder 2, cylinder 3. Okay, so cylinder 1 is the crank basically, so the angle of this is theta 1. Okay, so theta 1 is the crank angle for piston 1. So then theta phi 2 is the angle between 1 and 2 measured clockwise. So similarly, phi 3 is the angle between 2 and 3. Okay. So theta 1 is the angle of the crank, okay, the piston 1. So now here you can see the in plane position, okay, in side view. So you can see these are the 3 cylinders, 1, 2, 3. Okay. So now the resultant force is acting here. So this is the reference plane. So this is the reference plane is related to the cylinder 1. So this one is basically the line through the center of gravity of the engine. So the centroid of the engine here. Okay. So now the S represents the shaking force. Okay. So this shaking force. Now A1, A2, A3 are the distances. A2 is the distance between piston 1 and piston 2. So A3 is the distance between piston 1 and 3. So obviously the distance for A1 will be 0. Okay. Now AR is the resultant distance where the shaking force or unbalanced force is acting. Okay. So that is the resultant force distance to the resultant force from cylinder 1. So I go back. So the determination of unbalance or this shaking force. So in multi-cylinders engine is you can use analytical methods. So there are no graphical methods here. So we can see that the calculations will be very simple in terms of algebraic calculations. Okay. So here you're done in engineering dynamics. So the slider crank, right? The mechanism for your assignment, and you must have also derived the equations for the forces. Okay, I'll go through that. Here theta 1 is the crank angle of the first cylinder. So theta 1 is the crank angle of the first cylinder. So the first cylinder is at the front end, and this theta 1 is measured clockwise, so in the direction of the rotation. So when viewed from the front end. So basically the theta 1 will be known. So theta 1 is given for us. Okay. So now yeah, so this is basically an example of a 3-cylinder engine. So the front view and the side view. So basically you can see in the front view, so the theta 1 and this phi 1, phi 2, phi 3. So in this case phi 1 will be 0. So phi 2 is the angle between cylinder 1 and 2. So phi 3 is the angle between cylinder 2 and 3. So similarly, A1, A2, A3. So these are the distances, horizontal distances between the cylinders here. So if you recall slider crank mechanism which you have done. So if you, so this is your crank. So this is the connecting rod. So let us say this is your piston. So this is the angle theta. You can say A, B. So this is the piston C. Okay, so in this case, the force acting on the piston on the cylinder, so you can write this as mr omega square into, so you can write as cosine theta plus r over L. So r is the length of the crank, so L is the length of the connecting rod. Okay, so r over L into cosine 2 theta. Okay, so this probably you must have done in engineering dynamics course for assignment 2. So you have derived this slider crank equation for the force acting on the piston. So here you can see it all depends on the angle theta. So it has two functions. One is in theta, another one is in 2 theta. So now you can write this as mr omega square cosine theta plus mr omega square r over L cosine 2 theta. So you can write as two components. So the first one is called as the primary force. So this is the primary force. So the primary force, we call it as Fp. Okay. So this is based on the first harmonic. First harmonic means the angle is theta. Okay. So the second one is known as the secondary force. So we write this as Fs. So here the secondary force, because it is depending on the 2 times the angle. So basically the force you can write as the primary force plus the secondary force. Okay, so you call this as the resultant force. So you call S as the sum of the forces on the resultant force. You can write it as Fp plus Fs. So when you write sigma F means sum of forces, or Fr means the resultant force. So the resultant force is the addition of the primary force and the secondary force. So this is also known as the shaking force S. So S represents the shaking force. So please note that when we write the shaking force or the sum of forces, sometimes we also write the net force, all the same. So basically for a single piston engine, so the force has 2 components. So first one, you can call this as the first harmonic. So this is so this is known as the first harmonic, and this one is known as the second harmonic. So basically, we can simply say that primary force depends on the cosine theta. So the secondary force depends on the cosine 2 theta. So that is known as the second harmonic. So basically, the cosine theta, sine theta are known as harmonic functions. So harmonic functions mean repetitive functions. So you know the maximum value for sine theta, cosine theta will be 1. The minimum value is 0. So if you see graphical position for sine theta, cosine theta. So how does the graph looks for cosine theta or sine theta? So basically you can see it is just a repetitive function. So we say harmonic function. Okay. So when theta is 0 degrees, okay. So when the value starts 0, 1, 0, negative 1, 0. It repeats. So as the angle increases, so the magnitude oscillates between positive 1 and negative 1. So therefore the functions are harmonic functions. So repetitive functions. So theta 0 degrees, 90 degrees, 180 degrees, 360. So just go on adding up. As the theta increases, the function value always between negative 1 and positive 1. So that's why we call the primary force as the first harmonic, and the secondary force is the second harmonic. So now we know that when you are dealing with inline engines, multi-cylinder inline engines, so we can write theta as theta 1 plus phi. So theta can be written as theta 1 plus phi. Okay. So this phi can be, in a 3-cylinder engine you have phi 1, phi 2, phi. So in a 4-cylinder engine you have phi 1, phi 2, phi 3. Okay. So phi is basically the angle between cylinder 1 to 2, then 2 to 3, 3 to 4 like that. So therefore you can write theta as theta 1 plus phi. So once you write like this, then you can write now the sum of the primary forces. So sum of the primary forces. So you can write the sum of mr omega square. So we can write it, we replace theta. So we replace theta with theta 1 plus phi. So we write theta 1 plus phi. Okay. So mr omega square will be, I'm sorry, I need to write cosine cos. So please add cos here. So it should be cos theta 1 plus phi. So this one, mr omega square is constant. So depending on the number of cylinders, so now we can write this as cosine theta 1 plus phi. So you know that the trigonometric identity cos A plus B is equal to cos A cos B minus sin A sin B. So this is a trigonometric identity. So we are going to use this trigonometric identity to expand this term. So to expand this term. now we can write sum of the primary forces is mr omega square. Okay, so cos theta 1 plus phi, so you can write this as sum. Okay, cos theta 1 into cos phi minus sin theta 1 to sin phi. Okay, so we can now take out mr omega square. So theta 1 is the current angle, so which is constant. So we can take this cosine theta 1. Then you can now apply this summation to cos phi. So similarly, we can take sin theta 1 and apply the summation to sin phi. So this is because the cosine theta 1 and sin theta 1 will be constant for all constant. So now we can write the secondary forces. So this is the primary forces. Now for secondary forces, we can write sum of the secondary forces Fs is equal to, so mr omega square r over L. So you can write sigma cosine 2 theta plus phi. Now we write 2 theta 1 plus phi. So we can expand the same way. So cos A plus B as cos A cos B minus sin A sin B. So we can write this as, now I can multiply this r and r, so I can write mr square omega square over L. Okay, so cosine 2 theta 1 I can take out of the summation. So then I can write here cos 2 phi. So we can, just like primary forces, so we can also write for the secondary force.
So what 2 phi?
Because theta is equal to, so we have theta 1 plus phi, right? So 2 theta will be 2 theta 1 plus 2 phi.
Oh. I think your first equation, the 2 should be outside of the bracket, I think.
That's right. So I can write 2 here. So now, if we want the inline engine to be balanced, so for balancing, so for complete balancing, so sum of the primary forces must be 0 and the sum of the secondary forces must be 0. So for balancing means zero shaking force. So net force will be 0. So now you look at the equations. So how to make the sum of the forces to 0, and sum of the primary forces to 0 and sum of the secondary forces to 0. So you can see, let us look at the first one, sum of the primary forces. M r omega square, they are just the numbers or constant. So theta 1 is also constant, right? So cos theta 1 is just a number. So now you have to make cosine phi to 0, and you have to make sum of sine phi to 0. So if you make these two summations to 0, the whole primary force will be 0. Okay, so we can write sigma f of primary force is 0 implies, okay, so sum of cosine phi should be 0, and sum of sine phi must be 0. So similarly, sum of secondary forces to 0 implies, so sum of cosine 2 phi should be 0, and sum of sine 2 phi to be 0. So we know primary force and secondary force, so we can see that the net force is primary force plus secondary force. So for balancing, so to make these two forces 0, so if you can design the inline engine in such a way that some of these cosine phi angles, some of the sine phi angles 0, then the primary force will be 0. You can also make cosine 2 phi summation and sine 2 phi summation 0, so you can make the secondary force is also 0. Now after the forces, we also know that because of these pistons are located horizontal distance away from each other, so there will be movements developed. So similarly, you have the primary movements and secondary movements. So the primary movements are due to the primary force. So the secondary movement is due to the secondary force. So what is the primary movement? So sum of the primary forces multiplied by A. So secondary movement, sum of the secondary forces multiplied by A. So now we can write, so the primary movement Cp. So Cp is the primary movement. So we can write mr omega square into sigma A cos theta. So we can write this as mr omega square sigma A cos, so theta is theta 1 plus 5. So if you expand this like the previous one, so cos A plus B as cos A cos B minus sin A sin B. So we can write this as mr omega square. Then we can take out cos theta 1, and we can write sigma A cos phi. So minus sine theta 1 sigma A sine phi. So theta 1 sine cos theta 1 sine theta 1 are constant, so we can bring out of the summation. So now the summation will have only A cos phi and A sine phi. So similarly, we can write the secondary moments. Okay, so we can write the secondary moment. So we can write m r square omega square over L. Okay. Summation A cosine 2 theta. Okay, so instead of cos theta, we have A, okay, cosine 2 theta. So we can expand this in the same way.
Sorry, the CP, the last one should be NRW square A cosine 1, right? And there should be an A in front.
Because it's all multiplication, right?
Multiplication, yeah.
So the
Oh,
you're multiplying
oh.
with A.
Okay, okay. Oh, yeah, yeah.
So now you can write the same thing. Okay, we can expand this. So we can write CS is equal to m r square omega square over L. So now you can write cos 2 theta 1 sum of A cosine 2 phi minus sine 2 theta 1 sum of A sine 2 phi. So the resultant movement will be so we write resultant movement is primary movement plus the secondary movement. And if you know the resultant movement and the resultant force, okay, so the shaking force, so you can write the distance from the cylinder to the shaking force is, you can write C over S. So this is moment, resultant moment over shaking force. So if you recall, moment M is equal to nothing but F into L, right? So the force and perpendicular distance. So here, this L is the perpendicular distance to the resultant force. So therefore, we are writing M by M. So M is, we are writing here C. So the resultant moment. So S is the shaking force. So R is basically the distance to the shaking force. So where the resultant shaking force is acting on the inline chains. So now to make CP0, so the primary movement acting on the inline engines to 0. So what we need to do? We need to do sum of A cos phi must be 0 and sum of A sin phi need to be 0. So similarly, to make the secondary movement 0, so we have to make sum of A cosine 2 phi to 0 and sum of A sin 2 phi to 0. So that means if you balance any inline engines, okay, so it all depends on making the cosine phi or sin phi, cosine 2 phi or sin 2 phi. So if you make these conditions true, okay, then both primary force and secondary force will be 0, moments will be 0. So to make the primary forces and secondary forces 0, so you need to make sum of cosine phi, sum of sin phi to be 0, or sum of cosine 2 phi and sum of sin 2 phi to be 0. So normally in the exams, there's no need for you to derive these equations. So the most important things are now these are the conditions. So to make the resultant force 0, okay, so you have to ensure these conditions. So similarly, to make the resultant primary movement and secondary movement to 0, so you have to make sure that okay. Now let us go through the slides again. So here now we can see that the first cylinder is the crank angle of the first cylinder is θ1. Okay, so θ1 is the crank angle. Now with respect to θ1 in a multi-cylinder engine, so in a multi-cylinder engine, so the other cylinders are the orientation of the other cylinders are measured. So the angle between 1 and 2 is phi2, then 2 and 3 is phi3. Okay. Then the horizontal distances from cylinder 1 to 2 is A2. So 1 to 3 is A3. If this shaking force is acting here, so the distance from first cylinder to the shaking force is the resultant distance A. Okay. So now these are the equations which we have done now. So the inertial force you can write as mr omega square into cosine theta plus r by l into cosine theta. So this equation definitely must have derived in engineering dynamics. So in your second assignment of engineering dynamics, Snyder crank. So now we can expand this into primary terms and secondary terms. So first harmonic cosine theta, second harmonic cosine 2 theta. Okay, so theta and 2 theta. So then the net force is the sum of the primary forces plus the secondary forces. So the entire thing we call it as the shaking force or the resultant force or the net force. So to balance an inline engine, so you need to make the total force acting or the shaking force acting on the engine to 0 and also the total movements acting on the engine to 0. Okay. So now we expand this by theta, we write θ1 plus phi. Okay. And here we replace theta with θ1 plus phi. So then you expand this by the trigonometric identity. So now some of the primary forces we can write like this. Okay. So to make the primary forces 0, now we have to make sum of cosine phi to 0 and sum of sine phi to 0, because all other terms cannot be 0. So to make the sum of the forces to 0, so sum of cosine phi and sum of sine phi must be 0. Then the primary force acting on the inline engine will be 0. So it all depends on how the cylinders are oriented. So similarly, you can write sum of the secondary forces. So here you can see now sum of cosine 2 phi and sum of sine 2 phi must be 0 to make the secondary force acting on the inline engine to 0. So if you want both the primary force and secondary force to be 0, so then sum of cosine phi, sum of cos 2 phi, sum of sine phi, and sum of sine 2 phi must be 0. Alright, so now we can also write the primary moment and the secondary moment. So the primary moment is primary force multiplied by the distance A. So since you have many cylinders, so you have to now write this as A cos theta. Okay, so this is the primary force is mr omega square into cos theta, so multiplied by A. So if you expand this using the same trigonometric identity, so now you can see sum of A cos phi and sum of A sin phi. So if you want to make the primary moment on the inline engine to 0, then you have to make sum of A cos phi to 0 and sum of A sin phi to 0. So similarly, secondary moment, now you have sum of A cosine 2 phi and sum of A sin 2 phi. So the total moment acting on the system will be, so primary moment plus the secondary moment. Now once you know whatever the primary net force or the shaking force, and if you know the net moment, then the resultant distance can be calculated as C over S. So C is the total moment or resultant moment, S is the total force or the shaking force. Now let us apply this to an example here. Now you may look at this example, note down what are the values given. So there is no need to draw this figure, but you can just note down the problem. Now here the idea is the most important things are this. So phi 1 is 0. So this is, so that means for the first crank. So phi 2 is 270 degrees. So you are now doing, okay, a two-cylinder engine. So the cranks are at 90 degrees. So the two cranks 1 and 2 are at 90 degrees perpendicular. So you are asked to determine the shaking force. So the resultant distance, then theta 1, when theta 1 is 30 degrees. And the value mr omega square is given, so it's just a constant. Okay, R by L, the ratio is given. Okay, here A is given as 100 mm. So the horizontal distance between piston cylinder 1 and 2. So theta 1 is 30 degrees, phi 1 is 0, phi 2 is 270. So what is given? Theta 1 is 30 degrees. So phi 1 is 0 and phi 2 is 270. And A is 100 mm, or you can write it meters. Okay, so we can write now the sum of the primary forces. So we can write m1 omega square. So cosine theta 1 to sum of cos phi. So negative sine theta 1 into sum of sine phi. So now we calculate what is sum of cosine phi. Okay, so we can basically write cos phi 1 plus cos phi 2. So similarly, the sum of sine phi. So just calculate and tell me what is sum of cos phi and sum of sine phi. So Prabhu, you are recording everything in your brain. So generally, if there is no question on balancing masses, then you will be asked balancing cylinders. So one of the balancing question will be the fourth question. So sum of cos phi is equal to, so this is cos 0 plus cos 270. Cos 0 is 1, cos 270. So you will get 1, right?
Yeah.
Then the second one, so the negative 1. So now you can write sum of the primary forces will be mr omega square, okay, cos theta 1. So into sum of cos phi. Cos phi is 1, so I can just leave like this, cos theta 1. Then minus sine theta 1 into sum of sine phi. So minus 1. So minus of minus will be plus 1. So my primary force is equivalent to mr omega square into cosine theta 1 plus sine theta 1. So next we can write sum of the secondary forces. So sigma fs. So here we can write this as m r square omega square over L. So cosine 2 theta 1 into A this no A like this. Okay, cos 2 phi sine 2 phi. So here we calculate now sum of cos 2 phi, then sum of sine 2 phi. So cos 2 into 0 is 0 plus cos 2 into 270. So cos 540. So here sine 0 plus sine 540 degrees. So calculate how much you get. cannot do anything.
The
Yes.
first one is cos 0.
Because
Oh,
your
oh,
phi 1
yeah.
is 0, right? 2 into phi 1 is 2 into 0.
Both are 0, right?
Right. So both you get zeros. So that means the secondary force is 0. So that means the shaking force is only due to the primary force. So shaking force or the resultant force. So S is equal to, so we can write only mr omega square into cos theta 1 plus sin theta 1. So now we can do the similar thing for the moments. So for the moments, so the primary moment Cp. So Cp we can write it as mr omega square. So I write cosine theta 1 sum of a cos phi minus sin theta 1 sum of a sin phi. So now calculate what is sum of a cosine phi and sum of a sin phi. So you can just leave as A. So though the value of A is 0.1 meter, so you can just write it as A. So here you can write A cos phi 1 plus A cos phi 2. So A sin phi 1. So when you write here, you have to write A1 cos 1, so A2. So A1, A2. So A1 will be 0. Okay. So A1 is 0. And your A2, you can write it as A. So the value of this is 0.1 meter. So A1 is the reference point of the first cylinder, so it is 0. So hence answer for the first one?
This one is zero.
First one is 0, so it is like 0 into cos 0, cos 0 is 1, so 0 into 1 is 0, plus A2 is A, so cos 270, cos 270 is 0, so total you get 0. Now we are dealing with only 2 cylinders. Okay, if there are 3 cylinders, then you have A1, A2, A3. If there are 4 cylinders, A1, A2, A3, A4. So the second one. That will be negative A. So you can write it as negative A. So now you can write Cp as, so the primary moment as mr omega square. So cos theta 1 into 0. So since sum of A cos phi is 0, the whole thing will be 0. Then minus sin theta 1 into sum of this is minus A. So minus of minus will be plus. So you will have A sin theta 1. So the primary movement is simply mr omega square into A sin theta 1. So next we can calculate the secondary moment. So CS, the secondary moment. So we write the equation for the secondary moment. So we can write mr square omega square over L, then cosine 2 theta 1 into sum of A cos 2 phi minus sine 2 theta 1 sum of A sine 2 phi. So now can you calculate sum of A cos 2 phi and sum of A sine 2 phi? So any answer for the first one? Yeah, -8. So the next one is 0. So that means you can now write the secondary moment S is equal to, CS is equal to negative m r square omega square over L A cosine 2 theta. So we know now that so the shaking force S is equal to mr omega square cos theta 1 plus sin theta 1. Okay, so the moment C will be so Cp plus Cs, right? So the total moment is Cp plus Cs. So Cp is mr omega square into A sin theta 1. So Cs is negative. mr omega square over L A cosine 2 theta 1. So you can take mr omega square as a common. Then you can write sin theta 1 minus R by L cos 2 theta 1. So now we can write the resultant distance A is equal to the total moment over the total force. So moment over shaking force. So the moment is A mr omega square sin theta 1 so over the shaking force is mr omega square so basically you can cancel out mr omega square. So the problem given theta is equal to 30 degrees, A is 0.1, R by L ratio is given. R by L is 1/4. So you can calculate what is AR. And from the equations, you can also calculate what is the net moment, what is the shaking force, and you can also calculate AR. So can someone give me the answer for shaking force? Because mr omega square is given. Mr omega square given is 8,900 newtons. So, any answer for the first one? A, yeah, it's shaking force. I think the answer here is 12158 newtons. Is that correct? Then what about the movement, total movement? So, any answer for C? How much? 3? Yeah. So 33.75 Newton meters. Then what about here? So you can just divide by the two numbers also. So I think if you divide the two numbers, you will get about 27.5 mm. All right. Okay. So now the time is nearing 8:25. So you can go for break. So come back by 8:45. Okay. So we'll do one more question, then we'll have a quick revision. Okay. So either this type of question or the dynamic balancing.
Still come up there.
This is an important question.